Man, I should really get going on this physics project. It's gonna be due one of these days, and geez, I gotta get it done. Okay, so today we're gonna be looking at the finite parabolic well, or as I prefer to call it, the thing I just put on your screen. So of course, it's worth saying that this is obviously a quantum potential, and we're gonna be taking a quick look and see what we can get from this thing. So the first thing, it's sort of indicated by the name too, but you can, see that this is obviously sort of a combination between a finite square well and a harmonic oscillator sort of deal. And you can see that top term there is our harmonic oscillator, this expression right here that I just circled, and we can see that that's the case when this absolute value of x is less than or equal to some value a. Okay, so then we have on the bottom there, then when that's not the case, when x is greater than a, we have this constant potential v naught. So what we sort of expect to see here is a couple of a big parabolic sort of crater with two plateaus of v naught, this constant potential above it. And I'll just show you a quick look here of what I was able to create using my method of what I got this thing to look like, and it's right here, and it's pretty much what you'd expect. Yeah, so we want to use this potential, and we want to solve the Schrodinger equation numerically. So I'm going to talk about my method, how I used to do that. So as I said before, just a second ago in fact, we want to solve the Schrodinger equation, but we want to do it numerically. Well, that sounds challenging, of course, as you may be saying, because that means taking this evil second derivative right there. Well, there's a way to get around it, and that's what we're going to be talking about here with the method. For the method that I used, it's going to be what's called the finite difference method, and I'll go into a bit more detail talking about that right now. So I bet you're wondering, how are we going to deal with this, massive pain in the butt continuous second derivative? Well, the secret is we're not. Pretty much we're going to, try to approximate it in a way that's easier to deal with. So we're going to essentially, instead of saying it's one continuous, second derivative, we're going to convert that nice continuous thing into a sequence of points separated by a distance we call delta x. That's a small little distance between these points. And so by taking the derivative at each of these little points and factoring in, of course, our small distance between, we're able to find a finite difference, which is pretty much equal to what the first derivative would be, and then we can apply this further to then find our second derivative. And I'll show you. I'll have both of those on the screen for you there, I'm sure now. And yeah, so then from there we can, at each of these little points we're getting these values when you solve for the Schrodinger equation at each of these little points, which is great till you realize there's a lot of points. So what we want to do then is we can create a sequence of linear algebraic equations, which then of course we can turn into a matrix, so we will make our Hamiltonian a big matrix. And by finding, you'll have that on the screen now too, and by finding the eigenvalues and the resulting eigenfunctions, we'll find our bound state energies and our wave functions. And so that'll be on the screen for you there. Yeah, so then that's the method that was implemented to try to find the results that we have in this video here, and that'll be coming up right after this. So before I launch right into the results, I'll quickly just talk about some of the parameters I had to use. So from the first equation there, there's a lot of variables there, and so those I just set some arbitrary values for those. So for instance, a I set to a value of 5, so that means that big parabolic gap is 5x units wide. V naught is 10 atomic units, and then we had the mass I just had that as 1, just to make it simple. And then for omega I also just said that was 1, just to make things simple, easy. We get some nice graphs out of it. So I'll show you the results of that now. So what do our results look like? Well, so you can see from this plot here that we're getting pretty much what you'd think. Between that, -5 and 5 range, where, the absolute value of x will be greater less than or equal to A, we're getting simple harmonic motion functions pretty much. You can see them all there, except the exception to that is the E0, which is just a big exponential decay curve, it looks like. That's also expected. It's just, a little less clear to see that now. But yeah, I mean, we're getting what we think we should, right? And you can see there the energy values too. I mean, there's less of a baseline for those, but just trust me, bro, when I tell you that they're consistent with what is expected as well. They're in terms of atomic units, because it just ended up being easier that way to code them in for me. But on the terms of electron volts, it's on the magnitude of like 10 to 100 electron volts, which is pretty expected. Okay, so maybe you're wondering now, so what happens? I just chose these values randomly, these V naughts and A's and whatever. So what happens when you change them up? I am so glad you asked, because I did that, and we can see the results of that now. So you see that when you're looking at these change values, so you can see here, I put it on the screen, that, some weird stuff happens to the graphs. Like you can see, especially with the V naught equals 1,000. Well, first of all, E0 has finally joined the party. I'm happy for him. And you can see it's all just simple harmonic motion. There is nothing else really going on, to be honest. And that sort of makes sense. And why does that make sense? Okay, well, let's go through them really quickly here, because I think I'm over the time for this video already. But so pretty much, if we're looking at V naught at a high number, well, you're essentially just making those plateaus we mentioned at the start. You're making this escape energy for these things to get out of this big giant, parabola well. You're making it super high. So for the first 5 energy states, which I have on the graph here, it's essentially just a harmonic oscillator that they're sitting in, an infinite parabolic well. So then we look at, okay, so what's going on when we turn A into a tiny little number? Well, so you sort of think of, okay, so what's going on there as well? When V naught, in the V naught section, we just have a constant potential. That's great, whatever. So then what's going on when A shrinks to nothing? Well, essentially what you're getting is a big giant only plateau of V naught with a tiny little gap somewhere with a rate of width of 0.005. So it's essentially just a plane of constant potential, which we know is the same as a finite square well. So we're getting those nice sinusoidal functions that are indicative of that sort of thing. And then in omega, we're seeing, okay, that doesn't look too different. I mean, the amplitudes are a bit higher, the energies are a bit higher. And then, where's purple? Where did the purple thing go? Well, you can see it on the right-hand side, and you see on the energies there that its energy is 10 atomic units. Well, that's weird, because that's the same as V naught. And that's, so in this well, this certain system, in order for there to be a bound energy state, because this is not like a harmonic oscillator where everything is a bound state, these, in order to be bound states, need to be less than V naught. These energy bound states, the energy needs to be less than V naught. So in this case, when the energy got greater than V naught, it's essentially escaping that potential well. It's not going down there, or in a simplistic way of looking at it. Its energy is too high, so it's not involved in anything to do with the well, really. So it's not getting any of that nice harmonic oscillator curvature there. And so that's pretty much, I guess, all I wanted to say in terms of my results here. I guess I'll just quickly talk about it since I'm already going to be 10 minutes over. The uses for this, so there's been proposed uses for this particular system, or some variation of this system, in some biophysical context. So it's not like this is useless stuff we're looking at here. I mean, quantum mechanics is one of those fields that are just constantly getting new uses. So this stuff is useful to know. It's not just a thought experiment. And I guess I just wanted to leave off with that. So thank you very much for listening. Sorry I'm so much longer than I should be, but goodbye.